Welcome, friends. There we are. So we can do a little adjustment. Perfect. Ah, all right. Another Haskell hacking evening. Probably just going to work on more ESC challenges. I'm still up on that horse, but I'm kind of falling behind a little bit. So if you're doing the challenge too, you're past day 11. This could be no spoilers for you. But yeah, I think they're kind of fun. What we got? Some code. Maybe we'll do what we did last week and review some of the solutions. So last week was kind of funny. We didn't quite finish on the stream. Like we were like, it's just on the tip of my tongue there. I finished the stream. I looked at the code for like 5 seconds and it just went. So that was kind of fun. We're gonna fetch. And we'll pull that down. Yeah, so the solution ended up being that, well, first, yes, hash map is a fine way to encode our graph, but I'd gotten the arrows the wrong way. So I fixed that here. And everything was pretty much copacetti from there. Pretty straightforward. Part 2, a little different. It's 2020, 7. 7. Yeah. Part 2 was just like pretty easy as well. It was easier, I think, because I kind of knew what I was doing by then at that point, so I was able to put that one up pretty quick as well. Yeah, I don't know. Can't really say too much about that one. We just count the number of bags over the map. Adding the cost along the path, along the way. So that's why the numbers were there in the input. I thought it was going to be a weighted graph or something, but kind of sort of like that. So that was day 7. Day 8. Day 8. Let's see if I can remember what day 8 was about. Yeah, this was a pretty fun one. So in day 8, you had to take these kind of like very simple set of instructions. You got really 3: a no-op, nop, accumulate, and jump. And they give you a program that has an obvious flaw, or not so obvious to us, but an obvious flaw in that it has an infinite loop. And the first part of the problem was to find where the program breaks, essentially, where you detect the loop. And the way you can detect loops is if you encounter the same instruction at the same point in the program a second time. Now, I don't think that's generally true, but for this problem it is. So that's pretty straightforward. This is a pretty nice problem for Haskell, I think. And I just want to look at the code because that was a pretty good one. Advent. 2028. So I modeled the opcodes, the data structure with an opcode enum type thing. An op jump accumulator, just as we did before. We made an instruction, a tuple. You could have done this, like you could have done this in the data structure if you wanted to. I just put the ints there. I don't know why I didn't. I was kind of just going. Or maybe it'll become a little bit more obvious as we review this from your perspective. And maybe it'll still be a bad idea. I don't know. But a program is just a vector of such instructions, like just a straight array of some instructions. The idea is that you simulate the computer to run the program, so to speak. So I did that in a pretty stateful way using state monad. Okay, so you got a program counter. Right, so if you're running an emulator, almost every emulator you encounter is going to have a program counter. I'll tell you what instruction you're on. This is the accumulator, so that accumulator instruction is supposed to add its value in the instruction to this global accumulator. Then I kept the state, I kept the scene instructions we've seen so far as a tuple of the program counter value at the time we saw it and the instruction. So if we see that same pair again, then we're potentially looping. And then the program, the vector of instructions. So handy dandy initial loop state, pretty straightforward. Our program results just modeled as this is partly because I modified this for part 2. Yeah, so when I think I first did this, I didn't have this, but you don't really need it, but it turned out you need it. So if we hit an infinite loop, that's what I return there. Otherwise terminated or out of bounds. And so when you're running the state function, or the state monad, I should say, we pull out the state, and if we get an op out of our program from the program counter, match on. So this is where that, like, I pull apart the tuple here, the op and I. I don't know. I mean, at one point we're using guards here, so, and then we're case matching down here on the actual op. I feel like this is pretty okay code. So this is kind of like meta information about the different termination conditions we're looking for, like the, if we find the exact PC, the exact program counter and op that we've seen it twice, we get the infinite loop condition here. And this guard is basically the termination guard. There might be a code suggestion here. So we don't really need to do. That's cool. Redundant do. Get rid of it. Anyways, that's the terminated condition. So when the program successfully terminates, it's supposed to go to the last instruction and kind of go off the end. So if the last instruction happens to be an accumulator, we just accumulate that value before exiting. So it's fun. So the second part of that was basically breaking the loop. Figure out how to fix the program. There's one bad instruction in there that causes the loop. So you got to figure out which one you need to flip, and it gives you some rules about which ones you can flip. Basically turn a no-op to a jump, or a jump to a no-op. And you only have to do that for one instruction in the whole thing. And that's why having that enum turned out to be really useful, because I needed to basically do a patch, run the program, try a different variation, run the program again, try a different variation until we get the terminated condition. Luckily, we're guaranteed to get that. Yeah, checking if a program terminates is, in the general case, undecidable, so it's kind of fun to play with this one. Yeah. So that was 8, 9. What was this one again? So your neighbor happily enjoying the video game, turning your attention to the open data port on the screen, da-da-da. Oh, there's like a little... I think a theme of this is kind of... There's a couple puzzles like this I hear. Like cryptography kind of things. So... Hey Simon, how's it going? Can you repeat what your problem statement is? Yeah, I haven't started yet. I'm just reviewing some code. Hopefully you've been following along. I'm going to get to the problem in a minute. Unless you'd like me to slow down on this review. Let me know. That's fine too. So this is... The data appears to be encrypted with the Exchange Masking Addition System, XMAS. Which has an important weakness of ciphers. They kind of tell you what it is, and you have to figure out how to decode it, basically. Cool. Nice to see you, Simon, by the way. Thanks for stopping by. So yeah, our preamble consists of the numbers 1 through 25 in random order. To be valid, the next number must be the sum of those two numbers. So the idea is that you start off with a certain n, like 25, and you start at the 26 number and get the previous 25 numbers, or the prior 25 numbers, and you look for a pair of numbers in there that sum to the value at n. And then that's a valid number. So they give you the answer here, and this is for this example. So the first step in attacking this weakness in data is to find the first number in this list after the preamble, which is not sum of previous. So the first invalid number, following these rules. And then part 2, find a contiguous set of at least 2 numbers in your list, which sum to the invalid number from step 1. So this one was a good follow-on one, I think. Kind of like the... actually, 8 was good for that as well. I found this puzzle to be pretty easy. That one was in... yeah. 9. I think that one was pretty easy. I just wrote a function prior that does collect a value from the list and then the n values preceding it. If it's a valid XMAS number, I reused the combinations 2 function from an early puzzle, one of the first ones. So lazily generating the combinations of numbers and searching it for a target. So that one was pretty easy. Part 2, a little bit harder. This one was a little bit harder. I did it statefully again. I tried a bunch of different ways, and I was like, nah, I can't think of it. So I did it in a stateful kind of way where I just use I and j as vector indices. T is our target in the states, so then we just start at I, increment j, trying to search for a consecutive sum. If it's not there, increment I, and reset, start j from I plus 1, and go off that way. It's not the fastest. Well, it's... I think this one's slightly slow, actually. It's okay. Might be a better way of doing it, but maybe I was tired or something, I don't know. I'm not sure if I could even think of a better way, but maybe there is. Day 10 is where I started slowing down a little bit. So 10. The first part of this I found... Actually, this puzzle wasn't that hard either. I just started losing kind of interest doing it every single day. With the way my schedule works out, like I only have a couple of hours a night to myself, so doing these was taking up most of that time. Doing it every single night after programming all day, and you know, I just needed some time off away from doing these. So, anyways, this one was okay. It was pretty fun. It was pretty straightforward, I think. The idea is that you have to connect these numbers together in a certain way and count the differences between them. They give this really weird explanation, and I feel like if you try to read it, it might be a little bit confusing. I certainly thought so at first. I was like, what? Especially down here, like, look at all this. But the gist of it is that you got to put these in an order where the next number can only have a difference between n and n plus 1. Those two numbers can only be a difference of like between 1 and 3. And then you want to basically, to get the answer to your puzzle, you need to count the number of differences that are a 1 and the number of differences are 3 and multiply those together, I think is what they said, yeah. I think there might have been a bug in this. I'm not sure if there's a bug in this puzzle in general, but I've read some people's solutions to this after I finished it, and some people exploited the fact that they found that there was no differences of 2 in the whole list. So I don't know if that was intended or not, or if it's just some people's puzzle input happens to not have differences of 2, which could also be a possibility, right? So my solution for that was really simple. That's it. I'm not even sure if this is the most efficient way of doing it, but it's efficient enough. It finds the answer pretty quick. So just sort the numbers. Count the differences between them. Part 1 done. So the only thing is you have to count the differences that are just 1s and the differences that are just 2s, or just 3s. So I have separate fold functions for each of those conditions. I don't know, maybe there's a better way of doing it, but it was good enough. And yeah, the next part was a little bit trickier, but not too trickier. If you've encountered this before, it's pretty straightforward. If you know what this kind of problem looks like, it's very, very straightforward. But if you don't, I saw a lot of people chat about this one who maybe didn't, maybe struggled with this one a little bit. The idea is you want to find out how many combinations there are, valid combinations, or permutations, I should say, where you can use your adapters, all of your adapters in a valid chain. Right. So this is a permutation problem. Find the number of permutations from your input set. It could be pretty large. My answer was pretty big. So if you use the right data structure, it's actually really fast to compute. But if you try to brute force this, it's not going to be. And I guess this is probably where some of these problems have started ramping up a little bit in difficulty. This is what I would call a dynamic programming problem. So I'll just spend like a couple of minutes explaining this one. Just for funsies, and just, you know, doesn't take too long. So with this, let's look at just this sample input, right? The idea is that you want to find the number of valid permutations on those numbers. And if we map out one of these chains, like our valid chain, the one we know, the longest one, where we just sort the numbers, right? We start off at 0, because that's got to be the first number. It goes to 1. And then from there, we go to 4. And then we can go to 5. We can go to 6, 7, 10, 11, 12, 15, 16, 19, and then our last number is 22. That's one version of the chain. But from 4 we could switch from 5 because we can use a difference. The next number can be a difference of up to 3. So from 4 we can go to 6. We could also go to 7. Right? So from here, from 6 we can go to 7. And there's no 9, so there's no 8. So that's it. Right, 10. Right, once we get to 10 though, we can go from 10 to 12. I should probably put that on the other side, because we can also go to 11. Right, we have 11. And 12. Alright, so we also can go 11 and 12 here on this side as well. Alright, from 12 you can go to 15. From 15 you can go to 16. From 16 you can go to 19 to 22. 10, that's the 10 branch. I think we covered them all. It doesn't really matter if we draw the whole thing, but if you do end up drawing this out, the way you can tell you've got a dynamic programming problem on your hand is that you'll have branches of this tree that repeat themselves. So we'll end up with branches over there that repeat itself, we'll have branches over here that repeats itself, and so on and so forth. And so the reason why it gets expensive, and if you're just trying to naively brute force this, a solution to this, and it's taking a long time, is because you're recomputing all these subbranches all over the place, and the number of subbranches you end up with a large input grows exponentially. But they end up repeating themselves. They have common pieces. So if you've ever encountered, if you've been programming for some time, that you're not 100% new, and well, I shouldn't say it that way, actually, because you might not have encountered the Fibonacci problem. And if you haven't, bless you, you're pure. Fibonacci's used way too much, but it does explain this technique pretty well if you have encountered it before. The same idea there. You can graph out the Fibonacci numbers, and if you want to compute the 50th of them, you can do the whole graph just as we did, and you'll notice that there's lots of sub-branches. And the way you solve problems like this, generally speaking, is you memoize things. So when you memoize, you use a data structure to memorize the parts of the problem that you've solved before. Okay. So you need to be able to solve the problem for one part of your solution and then store that result in somewhere so that when you get called again, you can look in the store first before computing the answer, because you already know the answer. You've computed it before, you've memorized it. So that's what I did in chain combinations here. I initialize a hash map with our starting number. We know 0 is always going to be in there. And for some reason 1. At least for my problem set, you probably fix that, I guess. But the idea here is that we recursively fold, or just fold, count jolts over our list of numbers. And in this case, we look up, when we get to a node, a problem, a number, first we insert it into our map, and then we look up the previous 3. X minus 1, X minus 2, and X minus 3. That was the valid jolt connectors you can connect to, remember? Because you can only have differences of 1, 2, or 3. We look up their values in the map if they exist. Then we basically modify our current number with that value that we find. And so we build up the chain as we go down to the end, our sums of all the other branches. When we get to the end, we just take the last number we computed, and that will have our answer in it in the map. That's how I solved that one. Cool. So that's a little bit of dynamic programming in Haskell. There are lots of, I've seen quite a few different ways of generating these solutions. Some of them are, I didn't understand at all. Some of them are quite clever. Some of them are really straightforward. This one's a little bit messy, I found. It was kind of annoying to work with hash maps like this, in this manner. I feel like hash maps are a lot easier to work with in other languages, but they also have a lot more caveats. So you have to be a little bit more careful in Haskell. But for going fast, it's kind of annoying. A little bit annoying. I don't know. Pay the price, but it pays off. Sometimes. And I feel like some of the effort and some of the problems I've put into some of these solutions, like the parsing one from a couple weeks ago, it's hard to appreciate that's the solution to that problem, because like it parses into such a nice, well-typed thing that's correct by parsing it. It's correct by construction, which is a wonderful new thing to work with when you're building a larger system. But for these trivial problems, it wasn't terribly useful. But it was fun to do. So what can you do? So day 11, let's write some code. Let's kill a bunch of these. Okay. Day 11, I did take a look at the problem description for it not too long ago. Day 11, the seeding system. So this one, to me, it looks a lot like, if you've ever seen Conway's Game of Life, very, very similar. You have some kind of map with some kind of projection. In this case, I think it's an orthographic projection, meaning that if I take, orthographic. If I take one single cell in here, the neighborhood of surrounding cells that I'm allowed to look at are all the cardinal directions. So that's the top one, the bottom one, east and west, and then the diagonals as well, which is what makes it ortho, if I'm not mistaken. I might be mixing up my terms, but the idea is you can look at all the neighboring cells, including the diagonals. And so all the cells surrounding this one. And then you apply some rules to that cell to see if you should change it, essentially. So in this case, If the seat is occupied, we get an L character, and there are no occupied seats adjacent to it. So occupied seats, by the way, are going to be represented by these pound signs. And so if there are no occupied seats adjacent to it in its neighborhood, the seat becomes occupied. So in the next state, we're going to generate another map after applying all these rules to each cell. So it becomes occupied. If a seat is occupied, and 4 or more seats adjacent to it are also occupied, the seat becomes empty. Otherwise, the seat's state does not change. It stays whatever it is. So when you're building the next state, you just read from the old state. You don't change it and then apply the rule again to the changed state. You do the whole map and generate a whole new one for those rules. So we look at this one, and we look at all the cells like that. And if it changes state, we don't immediately recompute the map with that changed state and then look at the next cell. Just so, you know, it's one discrete change. Floors never change. Seats don't move. Nobody sits on the floor. That's extra fluff right there. So here's an example. After one round of these rules, every seat becomes occupied like this. And then, so that's one step of our function. Basically, to transform the input, it should end up like this. After a second round, the seats with 4 or more occupied adjacent seats become empty again. And so that's a step from this one, should return this. And the process continues for 3 more rounds. And here's what I think is kind of interesting about this problem, is that at this point, something interesting happens. The chaos stabilizes. Further applications of these rules cause no seats to change state. All right, so this screams like fixed point function to me. Right, if it's guaranteed to stabilize. I haven't fully written out a solution to this. I just looked at the problem description, so we're going to do it on stream today. But this looks a lot like a fixed point to me. If these rules are, I don't know, like, yeah. Okay, so co-metaнаds, I don't know a whole lot about. Would be really interesting. Yeah. Might even make it easier to do. I don't know. But I've never really used co-monads before. So it's going to be kind of hard to solve it with co-monads. Unless we can quickly get... Simon doesn't know either. That's okay. Where would we find out about co-monads? And if they could help us with this problem? Cats, co-monad. I think that's a Scala library. Haskell. Okay, well, we got a package, which probably means it's not going to have the greatest introductory documentation on it. Bartosz. So he has a way of explaining things that might not make it super clear if you're not a category theorist. Sometimes he does, though. We try that one. Yeah, so this is going to be pretty category heavy. It's part of his programming series, which is excellent, by the way. I don't know if I fully want to endorse Bartosz on my stream, but the content there is pretty good. School of Haskell. Pick of the week, cellular automata. Okay, Simon's sharing a link with us here. Yeah, so this is like cellular automata is exactly, that's what kind of the game of life is, and this is the general name for this kind of thing. So cellular automata in general are really neat things to examine. You can build self-replicating computers with them, which is an interesting idea. Not very practical, but pretty cool. Okay, so apparently they're the go-to example for comonads in Haskell. Perfect. Okay, control.monad, store. Ooh, function in our types, cool. And we could define an instance of comonad for that store. Extract and duplicate are the two methods, I guess, on the class that need to be defined. Alright, I'm not really sure what this does yet. A store describes some test that takes a configuration S and will produce a value of type A, where we also have some ambient initial configuration of type S. It is known, which we could start these. Okay. So immediately right off the bat, this looks a lot like what'll be our step function. And S is going to be like some kind of state. And then we run it. Kind of like the state monad, in a way. Yeah, why not? Is comonad built into base, I wonder? I don't know. That would be neat if it was. Let's try that. 2020. Here we come. Nearing the end, friends. Only a couple weeks left. Oof. I don't know how January 1st is going to feel this year, actually. I'm very tepid about it. I don't want to be hopeful. Just because, like, this year's been so rough. I don't know if I can bring myself to be fully hopeful, but at the same time, there's things to be hopeful about. We're on 11. Yeah. Okay. We can't find comonad in base. So it's a library. Good to know, good to know. Wait, I've looked at this library before. I just don't remember. Okay, I think this is the one we want. Let's add it. Comonad. Okay. Just build that. That's a very fun hat. I like that hat. Yeah, okay, so I haven't added derive functors. Fine. I know. I know I haven't added it yet, so I'm just going to add it here. That's fine. Yeah, I'm super happy that it sounds like the college is fully elected in Biden as well, so it's like super official now, I guess. Doubly official. But more importantly, to me at least, you know, vaccines are underway. The science has moved really fast on this, which is amazing. And from what I hear, a lot of people involved are not, like, you'd think the epidemiologists and well, all the people involved in producing a vaccine you know, they would be cautious about deploying a vaccine so quickly, right? There's been mistakes in the past, but they all seem very, very confident, which is good. Because they would be the first, I think, as an engineer, a software engineer, they'd be the first to criticize anything if they didn't feel good about it. They'd be like, So that's a neat development. Yeah, he does the Sideshow Bob bit. The mini rakes. Maybe. Kicking and screaming, who knows? Who knows what's going to happen? I mean, it's still... The reason why I don't want to be too hopeful about it, too, is that, like, it's not over yet. It's not like they've given up. You know, coups have come in pretty close sometimes. So, be careful, friends. Don't, you know... Don't sip the champagne yet, like you've won. But it's good progress. It's good to know. Whereas we used to say in martial arts, like, you haven't won until you've won. So don't feel like because you're doing well, you can get cocky or anything. You know? Okay, so it's built. Good. I'm chatting a little bit much here. That's good. That's okay. Let's see. Good. I'm happy with that now. Doesn't like that I'm importing it right that way, but it seems to go okay. Yeah. And I hope they win the Senate in Georgia and the Democratic senator there. And the runoffs and everything goes well for everybody there. We all, you especially, I'm sure, and everybody else, really, really deserve a break. Okay, so I guess it compiles, which is great. Okay, so what can we do with this? We don't have a solution yet. What do they suggest in this tutorial? Oh, yeah, nothing yet. Okay. So the experiment combinator characterizes a store completely. It lets you explore variations on the initial conditions of our test. Store gives you a little bit more power than we want in a cellular automaton, as you can do both relative and global addressing. I don't know what that means, but it happens to be very good general construction. Interesting little side fact, it's used heavily in the Lens library. I've been way too terrified to ever look inside the Lens library. There are some things man is not meant to know. Or people, humans. Maybe only commit and the maintainers are meant to know. I use Lens a little bit, but not very much. Maybe not as much as I could. Maybe for the better, because I don't know. People still find it's a bit of a controversial library sometimes, depending on who you talk to. In any case, a glimpse down the rabbit hole. So this is kind of what we're looking for. So like, yay! But so we import the control monad. Yeah, see? You're happy to use the magic. The magic is good. But if you stare too deep into the abyss, you're gonna be one of those people who can only talk about profunctors and optics, and nobody's gonna understand you anymore, and they're gonna put you in an asylum if you're not careful. It's understandable. I'm just joking, but yeah, it's. What I find funny about Lens is that it's when you strip it down and like you get that first introduction. Like Kemet gave a really good introduction to to Lens. I can't remember the name of it, the talk. But it starts with just a very simple new type, and it's totally comprehensible. But within 20 minutes, you're just like, I've lost you. I don't know what's happening anymore. Right, so it's like the very tip of the iceberg is very, very understandable, very, very simple. And you know, it's a thing, but I don't know, I'm afraid to look at that library on the internals. So down the rabbit hole we go. So we take an interesting exercise for the advanced Haskell is to flip the definition of experiment and take that as the definition for store. I don't know if I'm an advanced Haskeller, to be honest. But let's see if we can figure this out. So we have a new type now, a new type we're bringing in. We're bringing yet another language extension, rank n types. Oh, this is going to get fun fast. Pretext. Okay. With a function. It's for any functor f. We can have a function s2 f of s. And we'll give you an f of a. So if you give us an s, or if you give this function and some input s, we will turn that into an fa. And our experiment, there we go, takes that function, a pretext, and an f there. Why is it a particularly enlightening challenge? I don't understand. Why is that cool? If you replace the functor constraint in the definition above with applicative, you get a comonad I call the bazaar. This comonad is used to derive many of the most brain-bending traversal and unit play derived combinators in that. Simon, I don't know if we want to go down this road, man. I just want to solve a problem. This, oh no. What do we got to get to? The code for its comonad instance is identical to the instance for pretext above. It can also be made applicative. Uh-oh. How is this relating to anything to do with our original cellular automata motivating example here? Hopefully we're going to get to this soon. I'm getting impatient. I don't really care for clever tricks right now. So if you try to search for the store like analog of the bazaar, you wind you looking at what Twan van Laarhoven called a fun list. A non-regular data type challenge. It keeps repeating this over and over again. Okay, good. So an interesting exercise to derive, we're not going to do that today. Following the rules. Okay, so we can encode this family of two colored rules as a comonadic action. Rule W. Store f of s. Okay. Test bit W 0 to parts of take 3 bits. Oh, some lens action right here. Set that to whatever the hell this is. No, I don't got the memo. I have no idea. No. isn't the Stone Age anymore. Matt Sodil did a pretty good looking forest fire cellular automatic example a couple years back. Okay, that's good for that person. Okay. Now we have windows here we want. We'll turn window into a bunch of squares. Oh, fudge. Don't really care about that. I think this is just a little too clever for words. If I had time to sit down with this, it would be a fun read. I don't want to unpack it. I just want to understand how to write these rules and why we think it is a good idea. Nope, nope, nope. I don't like it. Too much. Sorry. This looks fun. But yeah, I don't think it's gonna help us. Yeah, I don't know. Like I can see what I can see what it's getting at, but it's just, yeah, like we're using lens already in traversals. Oof. That's kind of interesting, actually. From this though. I guess we could. I think we might be able to get somewhere with this. So I guess the idea is that if we write this step function, say, in our experiment, what is it going to take? A word 8, store s of bool to bool. So in our case, it might be something a little bit different, but the idea is that we can extend a rule in 10. We get a function from one world to a new world, which is what we want, like a step, where the rule has been applied uniformly across the entire world at the same time. It's kind of like what I was describing at the beginning there, when we're looking at the problem. Where does extend even come from? Is that another lens function? Maybe? Oh, jeez, I'm not even going to. Cool. Oh no, it's part of, I guess it's part of the package. Cool, man. Okay. Let's try it. See what happens. Yeah, maybe we learn a little. I don't know if I've learned. I don't know if that's been helpful to anybody else. to explain what comonads are. I'm still not sure. I don't get why it's cool, but I'm assured it is. Okay, so how would we even write our step? And what's our data structure to begin with? Probably want a hash map, I guess, to represent thing, even though look, it's using lists of lists. It's probably not good. At least an array or something like vector, but a hash map is also fine if you want to encode the keys as the tuples of the coordinates. Let's try. We could try this with a hash map. Probably not at strict each. I was thinking our would be a hash map of our coordinates. As integers to some char. Okay, so I was thinking that would be the grid. What does this rule do? So I guess it takes a char from our world, store s of bool, or a store s of our grid, and then a new grid. Does that make sense? I don't even know if that makes sense. Comonadic action. Store s grid. Putting a new grid. Yeah, I don't know. Store F. This will be our cell. What do we even got in scope here? It's there. It's there, I swear, but my tooling doesn't think it is. I'm gonna add it. Okay. So we have an S, that's just something. I don't know what that is, just an S. We have an F from S to grid. And we have a cell, char. Okay. We just have to, all we have to do is promise a grid. And I guess we've got to use F and S, and it looks like in the example here, I guess S is the state? Or the grid, the I have... So these got a num constraint on S, which is why you can subtract and add to it. What's this bool nonsense then about? Each bool... well, from numbers, his rules from 0 to 25, current cell, and the name of the left and right of it. We have 3 inputs to consider. Each is a bool, so we have 2 to the power of 3 different results to give. We bind all those values together as bits. Word 8, and the word 8 describes all possible 2-color cell automata that can look at the current and neighboring cells. Yeah. Yeah, cute encoding indeed. Yeah, I'll have to take a look at this sometime, another time. Feel like I'm just sitting here going, oh. And that's not a very interesting stream. We've only got 45 minutes left. So, cool article. Nice tip. Thank you, Simon. Let's learn about comonads sometime. What can we do instead? But just plain... I mean, that is plain Haskell too, but without comonads, because that's going to take me a while to grok. Okay, so we basically need a step function to translate from one hash map to another, and applying our rules. Its type would look like this. Grid to grid. And that's what its type would be. In order to implement step, we need a neighborhood function to get the neighborhood for a given cell in our map. And then the list of cells. Let's see. Grid. Location. And well, if you give me a bad location, obviously I can't get that. This is going to be maybe. Of ours. I think that looks sensible. If not spelled properly. That might be. Sets undefined. So you give us a grid and a location of that grid, and then I might return you Yeah, as long as it's a valid location, I'll return you a non-empty list of the neighbors around that point. So then, using that, we can probably implement a function that gives me the... We'll implement this rule. The seat is empty. There are no occupied seats adjacent to it. That becomes occupied. So, we want to find the number of occupied seats. Right, that would answer our question there for that rule. And if the answer is no, there are no occupied seats, then we can flip it. So, give me the grid, a location of a seat. Means you might give me a bad location again, so we're going to be stuck in maybe land. But this time, we return an integer. I'd really like that to be positive integer. An integer is fine. And that'll be the number of occupied seats at that spot if you give me an actual seat. And what else do we have? So if it is occupied and 4 or more seats adjacent to it are also occupied, the seat becomes empty. That can still be answered with occupied seats. Right? If we get with occupied seats come back with an integer, which we can ask questions about 4 or more, are you greater than 4 or equal to 4, then yeah, we can answer that one. So that becomes possible. And we can flip the seat to empty. Otherwise the seat doesn't change. Okay. I think we have what we need there. Let us just go to our specs. A11. Do we want to move these to a thorough module? Probably, so we might end up reusing them in part 2. So I'm going to put that in... Let's just call it grid. Actually, yeah, it's fine. Event Y2020. A11. Cool. Let us test this. Describe. But there's probably said this before, but there's one thing I've learned about doing this challenge is that there's really 2 key things. Get good sleep. And write some tests. Help you, or at least some way of verifying that you've implemented the right thing. It doesn't have to be tests, but that's what I've been mostly doing. Some days I skip them, but mostly write tests. It's been pretty helpful. On the days when I didn't write any, I think that's when I struggled the most. So let's describe a grid. It should return a valid neighborhood. Okay, so let's create a test grid. Probably have to import a module for. So we need to import that as well. Cool. So first things first is our location 0, 0. Let's make that an L. Let's copy paste that. 2, 3, 4. 4 is probably good. Oh. Make it line up. Say 4. 4 by 4? Probably good. Test out our stuff with. Maybe not good enough for testing some edge cases. But... yeah, I definitely should. Thank you for the tip, for the encouragement. In fact, another tip for streaming, stay hydrated. Which is odd. I mean, obviously getting good sleep is really important. I don't know about you, but with the pandemic and stuff going on the last couple of months, oh, sleep sometimes doesn't always come very easily. I think it's because of that, the background noise of all the things going on that have been going on. We do our best to self-care, but there's only so much you can do when there's like just this constant, what's going on? Stuff that some nights when I try to go to sleep, it just doesn't happen. But, you know, that's why you gotta stay healthy, exercise, stick to a routine, do what you can. But sleep is the best. And I think there's been like studies about it too, like across all of knowledge work, not just in software, but across all knowledge workers. The only thing that has a really large effect on productivity is a good night's rest. Number 2, I think, close number 2 is levels of stress. So we should turn a valid neighborhood. That would be good. So from our test grid, we should be able to call occupied, neighborhood. With our test grid, let's just get one of the middle ones. Colloquially, a grid. It's Y. We'll make sure the first int is the like x coordinate in the grid. And we'll start at 0, 0. Like that. Right? Okay. Cool. So this will be 1, 2, this will be the y-axis. Probably should have done this before I copy pasted, but whatever. And there. This becomes 3. Two, 3, and 1, 2, 3. Okay. So we'll our first test case, we'll grab this one. And that means we should get a list of 8 things. And these are all L's, so we could probably switch up our test map. A couple of these if we wanted to. So it should have 3 L's in it and 4 dots. So we're just going to trust that we get back something reasonable. So non-empty with length. Well, actually, we actually have to type this out explicitly, don't we? So it should be depending on how we order things. Might get 3 L's and 4 dots. Okay. Let's get our suite going. Checking the time there. So fast, file watch. This will error out, of course, at first. But then we can get our match going and get that running. Oh, sorry. Okay, our test list doesn't compile, which is pretty important. So let's import qualified hash map script as h. Oh, it's not a member, of course. Okay. Packages need test needs containers now. Leaking our data types and leaking our dependencies out. What can you do? Sorry, unordered containers. Okay, right back at you, GHC. There we go. And of course I wrote something silly. Thank you, GHC. And that's not test, it should be it. Okay, now everything should be good. Okay, we need the braces there. I was being a little bit too eager. Just because the non-empty constructor there. Okay. Boom. Get that going. Match. Oh, sorry. TA for test arguments. Not a huge fan of it to having to do it this way, but it's the way it is. Let's keep that quote there. Cool. One test failure because of undefined. Okay, let's implement neighborhood, shall we? Grid, our X and our Y. Okay, so all our target coordinates we can calculate off of this, pick them out of our hash map, construct our list, and we're done. The only thing if we ever encounter a case where we can't get it out, we should return nothing. So I think using our simple Haskell mini pattern, we'll use our do block, because a lot of the grid functions that look up stuff in the grid return maybes, which will be useful here. So that means we can get the only trouble with this is going to be naming them. We get top left, top right, or top left X, top left Y. Will be H dot look up X minus 1 and Y minus 1 in grid. So top middle X, top middle Y, same thing. This one is going to be just X and Y minus 1 in grid. Let's see, this one's going to be, let's kind of just go clockwise around the clock. Top right X, top right Y, maybe X plus 1 or Y plus 1. So middle left X, middle right Y, right. Yeah. Alan. It's in the middle. It's not the top or the bottom. It's the middle. Minus the left. So middle left, middle left. Good. Okay. That should be X minus 1 and Y. And then the middle right X and middle right Y. That should be X plus 1 and Y. And then the bottom row. Bottom left X. No, we're going to go clockwise. We're not doing clockwise, are we? Top right X. Middle right X. This one will be last, actually. Bottom right X. Bottom right Y will be X plus 1, Y plus 1. Bottom middle X, bottom middle Y. That'll be just X and Y plus 1. Bottom left X. Bottom right Y. Bottom left X will be X minus 1. That'll be plus 1. And then middle left X and middle left Y will be our last. That should be 8. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Okay, so once we've got all of those, then we can return our list. We'll start with oh, it's not returning a tuple. Oh, we didn't have to do all that. H.lookup's going to return the value, which is going to be the car. Okay. So, top left. top middle, top right. So Simon's asking, what Haskell mode do I use these days? For the past little while, because I'm lazy and haven't gotten around to it, I'm just using like whatever comes with Emacs Prelude right now. Just stock, pretty much. I was using Haskell Language Server, which is becoming so much better, and I do have a setup for it. I just have to get around to fixing this environment on this machine and just porting it over from my laptop. I just haven't done it yet. And I know, it's super lazy, and it's one of those things that it'll take me 5 minutes to do, but I run from it like the Dickens. I don't know why I do that. Top, 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 middle right, bottom right, bottom middle, bottom left, and then middle. Okay. Let me just go top middle, top right, middle right, bottom right, bottom middle, bottom left, left. Boom. I probably mistyped something, it looks like. That should be good. Nope. Got nothing. Okay, so X should be 1 and Y should be 1. And given to our neighborhood function in this case. So we -1 here. That's 0, 0. Yeah, we have a 0, 0 in our map. Should be that one. This is the only problem with this pattern, is that it fails simply, so it doesn't tell you a whole lot when it just returns nothing. X increasing, so we should get 0, 0. Alright, that'll be TL. TM is X, and that's going to be 1 and Y minus 1, so it's going to be 1, 0, so it should be this one. TR, that's going to be X plus 1, so that's going to be 2. Y minus 1, so it's going to be 2, 0, that's good. That's TR, so middle right, MR, the next line is X plus 1, so it's going to be 2, and Y, which is going to be 1, which should be this one. Bottom right, X plus 1, Y plus 1, that's 2, 2. Bottom middle, that's X, it should be 1, Y plus 1, should be 2. Okay. Bottom left, X minus 1 is 0. Oh, Y plus 11, there we are. Call stack, okay. I have heard other people chat about this in Haskell Slack a while ago. We should totally look that up and play with it sometime on the stream, for sure. Okay, so we expected something, but we got something else. So at least it's returning. It's not giving me the whole of the input. Oh, wait, maybe it is. Dot, 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 dot. So we got 1, 2, 3, 4. Did I double up on something? TL I used once. TM, TR, MR, BR, BM, BL, ML. So my test case is probably wrong. 2, 3, 4, 5, 6. Yeah, test case is just wrong. Okay, cool. That's done. Haskell stack. Cool. GHC.stack. Okay. This is 4.5. Neat. So, if I wanted to see this in action quickly, do I have to, is this in base? Let me pull that up again. Oh, it's internal. Okay, so it should ship with GHC. So if I have the right version of GHC, it should be in here. That work? Cool. I guess it does. And how do you use that then? Another retype class. You just use it like this. Just okay. Well, I kind of want to see this in action. So if I make this screwed up, it seems to just compile fine. I'm looking at old stuff here. Yeah, it should compile fine. If I make us an oopsie, is it going to display a traceback now? A call stack? That would be kind of cool. I don't know why this isn't tracing the bottom. Okay, it is airy, yeah, just like before. Well, it doesn't really do anything. Maybe you got to do stuff to make it work. At least I'm not under this test case. Huh. Well, thanks for the link, Simon. I will investigate that more. Need lookup to report there. Okay. Okay, so that's the neighborhood. Done. Now, using that neighborhood function, we want to implement occupied seats to get the number of occupied seats next in the neighborhood of a particular point. Okay, so in our map, for example, we don't have any occupied seats yet. So let's pick a spot. Let's put one down here in the bottom corner. Occupado. Okay, there's kind of one somewhat glaring problem with this that's starting to stick out to me already, is that this isn't Taurus, and they don't think they mention if this is a Taurus or not. Because right now, basically, if we try to get the neighbors of 0, 0, which is a valid thing to do, we're going to error out in our with our neighborhood function. Because we have to be able to get all of the neighbors. And if one of these fails, we don't actually want the whole function to fail. What we really want to do is just return the ones that didn't. So try writing a lookup prime function that takes the type class as a parameter. You mean the Haskell stack type class? Then you can return an either and put on the left part an error message containing the call stack. I see. Okay. Neat, thanks. For neighborhood, I think we're just a little bit too eager with maybe here. Maybe should really be reserved if you give me... yeah, if you give me a coordinate xy that isn't even in the map, we should return nothing for that. But these lookups for the neighborhood, I don't think should fail. And those ones should be just fine. So this is actually, I don't think it's quite right. Okay, so like lookup prime Haskell stack A with their hash map K of A. We return either string A. Okay, okay. So you'd use it like this, or GHC. What was it? Was it stack? Yeah, GHC.stack. Capitalized. Okay. And apparently you can write it like this. Haskell stack. Take an A. Take a grid. I mean like a key, okay. In which case our key type. Fix it. String or interesting. But to fix neighborhood now, I think the best way to do this is it should return a neighborhood on a corner. Still not empty, so that's still valid. A good type for us. So neighborhood and our test grid at 0, 0 isn't an invalid place to ask for the neighbors of. It should be. Now what should we get? We should get LL dot dot dot. Right? No, LL dot. Just 3. L. And the rest of the list, L and dot. Just like that. Welcome back, Simon. How's everybody else feeling tonight? Well, not a comma. It'd be nice to actually parse these into actual types, but whatever. Doesn't matter. Okay, so that should return like that. Okay, one failure. That's exactly this one should be failing. Okay, so to fix that, then we have the one case. We just have the case, the pattern match on, of looking up x and y in the grid. And then we just kind of return nothing, and I don't really care about the just case. That doesn't. I don't like it when I see this. All right. So we could instead keep our do block, but we'll just throw away the result of that look. We'll ignore it. Now the rest of these, though, are fine. So we can collect these into a list. And then we just have to prove, when we construct the non-empty list, that there's at least one element. Which will return a maybe as well. So that's fine. Yeah. Neighbors, ends. We could just do that with a let binding, I suppose, first now. Just take all of this. Inside some brackets. Braces. Maybe just once. Just do this. These cats. Okay. Such beautiful science. We really don't need to bind it. Well, except that we actually do want to filter this. So we're going to filter this with from justs. Maybe. I think it might have one that works over something foldables. Oh, look at that. We're starting to put them in the base libraries. That's call stacks right there. Nice. Yeah, cat babies. Okay. Sequence and cat babies. Sequence, I think, would be okay too, probably. Cat babies does the same thing as well. So we only want the just values, the elements inside our map. And then on empty as a constructor. For this as well. Did I skip it? I don't think so. Yeah, from list. It's a good convention to follow. A lot of the libraries follow it. I should have just guessed it. I should be used to this by now. Although it might be built into Reload. This Reload likes these. As typed. I'll put that over to the left a little bit. What does it like about that? What? The type of HL lookup, isn't it? It does return a maybe. I've never seen this error before. Because it doesn't know what this list is. Is that the problem? Are you really having trouble figuring that out? Okay. Cat maybes. Can I type apply? I think so.
Twilight falls on empty streets. I've seen it all, the days.
Do I need to import data dot maybe? I think this might be in Reload, but maybe I'm not. Maybe it's not.
I'm losing touch with everything.
Yeah, nice to see you, Kodak Troll, by the way. Hello. Let's get rid of this for a second. Okay.
Now I'm begging you to slow down, let me be alone now. I should be the last thing on your mind. It's been a long time coming and I'm still here running from
It still thinks it's a list of maybe car. Is the front list not the one I think it is? List done, not empty.
So just pretend I don't exist.
Yeah, so it's already in my prelude already. Although, let's just be super explicit for a second. Put that here. Qualify that. I couldn't actually expect to type maybe listen maybe car. Maybe sorry, maybe I'm misunderstanding cat maybes. Maybe we should use secrets. Just 1, nothing, just 3. Oh, look, they have the extra type annotations there. Maybe that's just what we're missing. Like, it can't figure out what the type is, which is kind of what it was saying. I don't think it's right. That is the prelude. Like this is child. Yeah. Gross. Ew. I don't like it, but it works. In which case we don't even need the little binding or anything else, but ew. Ow! Haskell! Why? Why are you doing this to me? Now you're doing it again. Oh my god, Haskell, why did I die? Ah! Let's just go back to the silliness we had before. Okay. Whatever. Whatever. It's fine. It's okay. Sometimes you get a few imperfections in your painting. Doesn't ruin it. Adds character. Oh, sorry to my claw. I can improve the font size. Hopefully that's better. In fact, this is probably only buffer local, so I may end up having to resize things as I go and flip around. Hopefully you can see that now. Right, so we have our neighborhood function, which is good. That can look into a corner now without throwing an error. Now I think we're ready to for my occupied seats. I'm glad it's working. So let's get that going. A number of occupied seats. Right, so basically if we go with our occupied seats function in our map, we can give it 3-2 as an input, and that'll give us 1. We can give it 2-2 as an input, it should also give us 1. So let's just give it a good old 2-2. I don't know why it's good or old, but it is. And that should be, yeah, just an integer, so that should be 1. 1 occupied seat. And that should fail. Of course, I will take a sip of water. We're a little over time tonight. That's okay. Feeling good, feeling strong. We'll implement occupied seats and then call it a night. Okay, so occupied seats. Let's get our grid. Let's pull out our coordinates. Okay. First things we're going to do with this is that we're going to look up the neighborhood of... So I might actually just do this. Neighborhood. Grid. Chord. Alright. And that's going to return back a list that we can... So we're going to reach into the list, F mapping over the maybe, reach into the list, and we got a function here we need to return. That's going to take a non-empty car to an int. Occupied seats. Pretty straightforward. Let's do that. Hopefully the audio mix has been alright tonight too. I assume so, because everyone's been talking back and forth with me here, so... But if it could use some tweaking, feel free to let me know. It's all good. So yeah, basically we're gonna fold over this non-empty list and just count the sharp characters. I think non-empty prime is gonna give us that one. Our starting will be 0. I like the valid whole fits. Hash with salt. If you haven't seen it yet, it's really cool. Isovector, who's been in the chat a couple of times, has been working with Reed. I don't know if he's been on my stream yet. At least maybe not in chat. Maybe he's been lurking, but they've been working on a tactics engine, a tactics plugin, really, for GHC, where it can give you really smart, it can fill in code for you and give you really smart, pretty decent code. Just using holes and type information. I really want to kind of give it a test drive sometime. It looks really fun and something that would be really, really productive for puzzles like this. Alright, so fold L is going to take our... Sorry, it was a car int car. Yeah, so we're accumulating int count car. And then essentially, if that car is sharp, we can do this with an if condition, I guess. Then we return count +1. We just return count, we'll skip over it. And a word wrapping there, so we'll just get rid of that. You can see it there. Good, good. Save that. I think we should be good to go on this one. Green, green. First try. First try. Let's go. First try. Boom. Occupied seats. Okay, that went really quick. Maybe we can do a little more. Okay, so that's like a good amount of the functions we need to implement our two-step rules to update our grid. So, how could we encode our rule as a function? Maybe that's what we should do using these newfound powers we have. So the puzzle calls it. So if seat is empty, there are no occupied seats adjacent to it. Seat becomes occupied. So we'll call that the unoccupied rule. Then we do the occupied rule. And otherwise, no rule. The null rule. Occupied. What's its type going to be? Probably... What should the rule even do? It's gotta know... So its job is to flip... Yeah. So if the current... It's gotta look at the current state of a cell and determine if we should flip it to occupied. So the unoccupied. So that means it's going to need access to the grid. So we might even just have the grid and the location. And returns another grid. Does that make sense? I think that makes sense. And then the occupied rule, if I could type, we have an exact same type signature. So using our grid and the coordinate, location, coordinate, whatever, using those terms interchangeably. The rule is, so there's no occupied adjacent seats. So first we have to get the grid. And of course, again, because we're dealing with accessing it directly, it's going to be a maybe grid. So this time we actually do want to get the seat out. Coordinate in our grid. And we want a case match on that, so we can actually get rid of this. That'll be... Oh. Yeah, if it's nothing, it'll just be nothing. If it's just a sharp, or just an L, that's good. And if it's just anything else... No bueno. Not a seat. That's pretty much all we can say about the cell. In switch case, these are kind of both matching branches, so let's just move this one up to the top. And just... At least get rid of a line there. Okay, so in the case we do just have an L. I can see where we can restructure this, but let's just finish the thought first. We get our neighbors. So the occupied seats around the coordinate. Of that seat, and if it's the value of that is equal to, well, that's a maybe int, so that's equal to just 0, then we're good. Otherwise, no way. That should be an arrow. That should be an arrow as well. Yeah. Okay, and if it is 0, then that cell, we adjust the grid. I think adjust. Adjust. I think that returns. I guess it's like that. No, that's not gonna do it. Just whatever. It's fine. Oh. Derp. Okay, yeah. Maybe grid. Okay, that's good. H dot adjust. Type it out. Snap the scope. Of course. Okay, it just returns the hash map. Yes, we'll still have to wrap that up. In this case. Maybe not adjust, maybe we could do update. Update. A to maybe a of our key coordinate. And this can just return constantly. Just why is this not cool? Oh, I didn't give the grid. There we go. Okay, so I think that's pretty much good there. Yeah. So let's just clean up that code. So our lint already is offering us a couple of things. That's got a redundant do. Of course, we don't need that. I think there's probably something else we could do with this here, because we're looking up over this. Get F map over that. Comment this out for a second. And we have car to grid. Group unoccupied. Now, because we get the car here, we can pattern match on it. Or something. And otherwise... yeah, that should be fine. Okay. Or not. Oh wait, it's got to return a grid. No, maybe grid. Yeah, so... Maybe we can't get it. Maybe I can't go about it that way. We're not... what is it? What card grid? So it's giving us the character in the grid. We have to return a grid when we F map into it. Does that make sense? Because this pattern match situation here makes me feel like, nah. Right, there's no sensible grid we can return there. Yeah. If we return just grid there, then we're always going to get back a grid. Even if we make a nonsensible check for unoccupied here. Which is not quite what I'm going for, so... In this case, we get the maybe card, a maybe grid. So we can still pattern match out here, but we have the opportunity to say, like, this doesn't make sense. A little bit more like our previous code. Maybe just a little bit cleaner. Ooh, Swarm Collective, Barry, how's it going, France? Thanks for dropping by. Yes, I work with Barry now. Barry joined our team. We program in Haskell. It's great. So, thanks for coming, Barry. And thanks for everybody else for following along. We're working on day 11 of the advent of Haskell, and we're kind of getting to the end of the stream actually, so it came at just the right time. But I'm continuing on for a little bit here. I'm trying to implement the occupied rule and the unoccupied rule, or maybe the other way around. Maybe you should wizard stick, and you can remind me to always take a sip when I'm going to be dehydrated. Oh, the age-old Vim versus Emacs battle. Man, that war has been going on for a very long time. A very, very long time. It's a bitter, bitter place. Yeah, so in this case here, we can kind of just copy paste our graph. I'm not even sure I like this even better than what we had before, but it's okay. But this returns into an equal sign. Yeah. Still not sure this is better. Just kind of an odd function. Not gonna line those up. Really. Oh, they are if it wasn't wrapping. Just looks weird. Cool. What's the unoccupied rule? Are we actually testing that properly? I don't think we actually have a test for that one. Let's make sure. Test the... Should apply the occupied rule. So, if anybody who has joined, if you have a good tutorial on comonads, send it my way. We're curious at the beginning of the stream. It's something I've heard other people say that for these kinds of problems, like comonads, cofunctors are the thing when you're trying to mutate grids and stuff like that. The tutorial you found was a little bit impenetrable for this stream, so I might need to give it a bit of a read. But if you have a lightweight one, that would be great. Otherwise, I'll probably digest it on my own time and come back to you and Maybe we'll refactor this puzzle to use comonads. But for the most part, I think it's a commit blog post, and I just started drooling halfway through. It was super fun that way. Okay, so the occupied rule means that we should be able to give here the test grid. Now, a place where it will apply. Right, that's the one we're working on. Oh, we're working on unoccupied, sorry. So an unoccupied seat. If it has zero occupied seats around it, and then it will become occupied. So, I think we got a place in our test map to test that out. Pretty simple. We can test that at 0, 1. Oh no, that's not actually a seat, so that'll return nothing. This one will become occupied. 0, 0. Should be. And that'll become... Oof, I gotta write out test grid again, but with the character flipped. This is where you want lenses or something. Good night, Simon. Goodbye, Barry. Thanks for stopping by. Well, let's just try copy pasta that to get through this. And this one will be turned to a sharp. What did I do? I edited the wrong one. That's fine. Test grid. Fine, I'm down here, friend. And this should be green. It's not. What did I do wrong? I expected a grid. That means I actually implemented the function wrong. Oh, maybe grid. Oh. Yeah, I also meant unoccupied. Now, this is better. Green. Yeah. Wrote the test after. Got it green right away. Okay, similarly, I think applying the other rule should be pretty straightforward. I mean, we'll have to test edge cases, maybe. But I think this is right. And then, it should just be a matter of folding all of these to generate a new grid. So let's test the occupied rule this time. On test grid. And the occupied rule says that, so we'll do it at 3, 3. And the occupied rule says that if this seat has fewer than 4 occupied neighbors, then it'll become unoccupied. So that should be... No, it's just I'm trying to be lazy. Bam. Alright, that should fail because we haven't implemented it yet, but I think the structure's going to be very, very similar. Yeah. Okay, so let's fix that. Grid. Board. Almost exactly the same, right? With occupied. means if we get just a sharp, that's the one we're looking for. The occupied seats is... we have to say less than or equal to 4 inside this maybe. Okay, that's the only tricky part of that one. But then we update it to flip it back to unoccupied. Everything else is nothing. Okay, so I think we can do maybe just less than equal to just to 4. And that needs to be maybe. It might actually work. Might not be that tricky. I'm gonna psych myself out. Oh, no. Let's see. Cool. Okay, that's the right test spec, right? Unoccupied rule. Ooh. Sorry, might have been a... Yeah, no, this is the unoccupied rule. Okay. All right. Sorry, that is a test error. Okay, that was the first thing that entered my mind there. That should be green. Yeah, cool. Yeah, and then the next step to finishing this part of the solve is to get a step function based on our 2 rules. So folding over our input grid, all of the rules, combining them together, and as we fold to get the new grid, and that should be that, and then we can write the solution. However, I'm out of time for tonight, so maybe we'll code review that next week, which might be my last stream of the year. So if you like what you see and you want to, you know, get notified when I'm streaming next week, give me a follow. Thank you very much, Nully, for the follow, and you'll be notified. Have a good night, Wizard Stick, and everybody else, and Nully, and may all your monads be free, and may your types always check. Peace out.